Welcome back to The Deep Dive. Today we're taking a look at a subject that feels incredibly futuristic, but when you peel back the layers, it's actually grounded in something pretty ancient. We're talking about artificial intelligence, but we aren't talking about the code or the chatbots or the sci-fi stuff.
Right. We're talking about the physical reality of it.
Yeah.
The part that almost everyone ignores.
Exactly. We get so caught up in the magic trick that we forget to look at the machinery behind the curtain.
Completely.
There's this huge misconception, and I think I've been guilty of it too, that AI is this weightless thing. It lives in the cloud, right?
Great.
It feels invisible. You open your laptop, type a prompt, boom, magic happens. It just feels free.
It's the ultimate illusion of the digital age. We use words like cloud or virtual, which, implies they don't have mass or weight. But if you actually trace the wires, the cloud is arguably the largest industrial project in human history.
Wow.
It's rows and rows of concrete buildings filled with silicon, copper, steel, and just massive cooling fans that generate a ton of heat.
And that brings us to the central theme of the research we're looking at today. It's a pretty stark realization. AI isn't just a software story anymore.
Not at all. It is fundamentally an energy story.
That's the shift.
And that's our mission for this deep dive, to connect the dots between that little text box on your screen and, say, a nuclear power plant in Pennsylvania.
And the insights are coming from a set of investment notes, an analysis titled AI Literacy for Investors.
Yeah, we're going to use them to trace the physical footprint of a single ChatGPT query. We're going to look at why the world's electrical grids are really groaning under the strain.
And of course, follow the money. Because if electricity is the new gold, we need to know who owns the pickaxes.
It sounds like a stretch to connect a haiku generator to a potential grid collapse. But as we'll see, the connection is direct, and it is immediate.
Okay, so let's unpack this. I want to start at the very beginning. I'm sitting at my desk, I open an AI tool, and I type, "Write me a haiku about a sandwich." It feels instant. What is physically happening in that split second?
Well, it feels instant to you, but you've just kicked off a pretty intense industrial process. Your request travels through the internet to a data center.
Okay.
Now, you have to visualize a massive building-like warehouse-size packed floor-to-ceiling with server racks. And inside those racks are thousands of specialized chips.
UPUs, right. Graphics processing units.
Exactly.
Now, I've heard of GPUs for gaming. My kids need them for their PCs. Why is AI using video game chips?
It all comes down to how they handle math. A standard computer chip, a CPU, is like a really fast race car. It's amazing at doing one complex task very quickly. It's sequential.
So the CPU is a Ferrari.
Right. But a GPU is like a fleet of 1,000 buses. They aren't as fast individually, but they can move a massive amount of cargo all at the same time.
Parallel processing.
That's the term. It was originally for rendering millions of pixels on a screen for a video game. But it turns out that the math behind AI works the same way.
So AI is just a massive pile of math problems that need to be solved at once?
In a sense, yes. When your request hits that cluster of GPUs, the AI model wakes up. These models have hundreds of billions of parameters. You can think of them as the model's brain cells.
Okay.
And to answer your question about the sandwich, the system has to run calculations across all those billions of parameters to predict the next word and the next and the next.
And it does this for every single user, every single time.
Every single query. And every calculation requires a jolt of electricity. Multiply that by hundreds of billions, then by millions of users, and, well, you start to see why the lights might flicker.
That is wild. I always assumed it was like a Google search where it just goes to a library and pulls a file that already exists.
No, and that is the critical difference. A Google search is retrieval. It's fetching a book. AI is generation. It's writing the book from scratch every time.
Which brings us to a distinction in the notes I found really helpful. Training versus inference.
Right.
Can you walk us through that?
Sure. Think of it like a professional athlete. Training is the boot camp. This is where engineers feed massive data sets, basically the entire internet, into a neural network.
So it's learning.
For weeks or months, it's just crunching data to learn patterns. This is a heavy, heavy lift. The analysis notes that training just one large model consumes tens of gigawatt hours of electricity.
I have no context for that number. What is tens of gigawatt hour?
That's comparable to the annual electricity consumption of a small city.
Wait, a small city's worth of power just to train one model one time?
Before anyone even uses it, yes.
That is staggering.
It is. But here's the aha moment from the research. While training gets all the headlines, the second phase, inference, is the sleeping giant.
And inference is the daily use.
It's the athlete actually playing the game. It's you asking for the haiku.
But individually, those must be tiny, right?
Individually, yeah.
Yeah.
But collectively, it adds up fast. The source material estimates one AI query uses about 10 times the electricity of a standard Google search.
10 times. So I swap my Googling for chatting. I've just increased my energy footprint for that task tenfold.
At least. And now think about the volume. ChatGPT hit 100 million users faster than any app in history. Companies are embedding this into everything.
Word, Excel, all that.
Exactly. The research suggests that the energy from inference, just the daily use, is going to surpass the energy from training within just a few years.
That makes sense. Training is a one-time cost, but inference is forever.
Precisely. It's the difference between building a factory and running that factory 24/7. And we're running this factory very, very hard.
So let's talk hard numbers. How much power are we actually talking about on a global scale? Is this a rounding error?
It is far from a rounding error. In 2024, data centers globally consumed roughly 415 terawatt hours. That's about 1.5% of all global electricity.
1.5% sounds small.
It sounds small until you realize that 415 terawatt hours is more than the total consumption of many mid-sized countries. It's more power than Italy or the UK uses in a year.
Wow.
And it's growing fast. But with AI, that growth curve is going vertical.
I saw a stat in the notes about the U.S. specifically, something about a bull case scenario that honestly sounded terrifying.
It's startling. The Lawrence Berkeley National Laboratory ran the numbers. In 2023, data centers were about 4.4% of U.S. electricity. By 2028, just a few years away, their bull case scenario estimates that could jump to 12%.
Wait, 12% of all electricity in the United States? 1 out of every 8 light bulbs worth of power.
Going just to data centers, yes. And to give you the raw numbers, demand is projected to jump from 19 gigawatts in 2023 to 35 by 2030. That's nearly doubling the load in 7 years.
Okay, so this brings up a massive question for me. Usually, technology gets more efficient. My phone battery lasts longer. My LED bulbs use less power. Why isn't AI getting more efficient?
That is the paradox here. We are seeing some efficiency gains, but the power density is increasing way faster.
Power density.
Yeah. The source material explains it really well. A traditional server CPU draws maybe 200 to 300 watts.
Okay.
NVIDIA's latest AI chips, they're drawing over 700 watts. And their roadmaps see chips exceeding 1,000 watts.
So the chips themselves are just hotter and hungrier.
Much hungrier. And it's not just the chip, it's how you pack them. A standard server rack for, storing your photos might need 6 to 8 kilowatts. An AI server rack needs 50 to 100 kilowatts.
That's a tenfold increase in density?
That's it. And the core issue is that the AI models are growing faster than the chips can optimize. To get a smarter AI, you just need more computation. There's no way around the physics.
More thinking equals more heat equals more power.
You got it. The industry is effectively becoming less energy efficient at the hardware level because they're chasing performance above all else.
So we have this insatiable demand for power. My next question is obvious. Can the grid handle it?
The short answer from our source is no.
Comforting.
It's the reality. The U.S. grid is aging, it's fragmented, it's been underinvested in for decades. It was designed for demand to grow maybe 1% a year. AI has just shattered that.
We're already seeing bottlenecks, right?
Oh, yeah. Northern Virginia, which is basically the data center capital of the world, is seeing massive delays. Texas, Arizona, same story.
And when you say delays, what does that mean? Can't these companies just pay to upgrade the lines?
It's not just about money. It's about physics and regulation. We're talking about single campuses requesting hundreds of megawatts. That's enough to power a small city.
For one building.
For one building. The utilities look at that and say, we can't get you that power for 5 years. We have to build new substations.
So what happens? Do the tech giants just wait? I can't imagine them sitting on their hands.
No, and this is where it gets really interesting. We're entering a Wild West phase. The tech giants are bypassing the utilities. They're going behind the meter.
Behind the meter, explain that.
It means they are cutting deals directly with the power plant owners to take the electricity before it even hits the public grid.
Oh, wow. So they're cutting the line.
They're buying the source. Look at Amazon. They signed a deal with Talent Energy to get 2,000 megawatts directly from a nuclear plant in Pennsylvania. They bought a data center right next door.
Just to plug straight in. That's wild. And speaking of nuclear, wasn't there something in the notes about 3 Mile Island?
This is the ultimate historical irony. Microsoft signed a deal to restart the 3 Mile Island nuclear facility.
The 3 Mile Island, the site of the worst nuclear accident in U.S. history.
The very same. They're bringing Unit 1 back online specifically to power AI operations.
That just shows you the level of desperation.
It does. They're realizing that wind and solar are great, but they fluctuate. AI needs 2047 relentless baseload power. And nuclear is one of the few things that provides that carbon-free.
So big tech is becoming the new energy barons.
They have to. If you don't have the power, you don't have the intelligence. It's that simple.
I want to play devil's advocate here, because
Yeah.
I feel like we've heard this before. People said the internet would melt the grid. They said streaming video would crash it. Why is the analysis saying this time is different?
It's a very fair question. But the source material breaks this down into 3 specific reasons why AI breaks historical trends.
Okay, hit me with number 1.
Number 1 is the rate of growth. Previous tech waves grew energy demand by single digits. AI power demand is growing 20 to 30% annually. Efficiency gains are, 5 to 10%? The math just doesn't work.
Okay, so the speed is the problem. It's moving faster than the concrete can be poured. What's number 2?
Number 2 is physics. We talked about the chips. Traditional computing followed Moore's law. Chips got smaller, more efficient. But AI is GPU-bound. These chips are optimized for throughput, not efficiency. The analysts call it the thermodynamic floor.
Meaning
There's a physical limit. You cannot manipulate information without creating heat. We're hitting the point where to do the math, you must burn the watts.
you can't code your way around thermodynamics.
You can't. And number 3 is additive demand. This is the subtle one. When we moved to the cloud, we shut down a lot of old servers in office basements. So cloud computing was often replacing inefficient energy use.
Right, it was substitution.
Exactly. But AI doesn't replace anything. It sits on top. You still use email, you still watch Netflix, and now you're adding AI on top of all that. It's purely incremental demand.
So it's not swapping an old gas guzzler for a Prius. It's keeping the gas guzzler and buying a tank.
A tank that runs 24/7. Precisely.
So what does this all mean for the listener? If energy is the bottleneck, who holds the keys? Where's the money moving?
The source calls these the picks and shovels of the AI revolution. Everyone's looking at NVIDIA, but the smart money is looking at the plumbing. The report highlights 3 companies that represent 3 ways to play this.
All right, let's run through them.
First up is the problem of baseload power. If you need power that never turns off, you look at Constellation Energy, ticker CEG. This is the nuclear play.
Because nuclear just hums along day and night.
Right. They're the largest producer of carbon-free energy in the U.S. Their fleet operates at a 98.8% rate. That's incredibly reliable. Constellations is sitting on the most valuable asset in the game, functional nuclear reactors.
Okay, so that's the power source. What's the next problem?
The second one addresses the physics problem, heat. The company is Vertiv Holdings, ticker VRT. This is the thermal play.
So they're selling the air conditioning.
Basically, if you have a chip running at 700 watts, which is a toaster oven, you need to cool it or it literally melts. Vertiv makes those advanced cooling systems. They're NVIDIA's primary partner.
If you buy the chip, you have to buy the fridge to put it in.
You got it. And the third addresses the sustainability problem. The company is Next Era Energy, ticker NEE. This is the renewable play.
But didn't we just say renewables aren't reliable enough for the baseload?
They aren't. But remember, all these tech companies have strict carbon-neutral pledges. They can't just burn coal to run these AIs. They need massive amounts of green energy to balance their books.
So they buy the credits.
And NextEra, as the largest provider of wind and solar, captures that demand.
So Constellation for reliability, Vertiv for the heat, and NextEra for the green credential.
That's the ecosystem. These are the companies enabling the AI race. Without them, the software stops.
It really changes how you look at the industry. We get so caught up in the magic of the AI, we forget the machine needs to be plugged in.
That's the big takeaway here. The limit on AI growth isn't code anymore. It's not even the chips, really. It's electricity. The electrons are the scarce resource.
It's a sobering thought.
And here's a thought to leave you with. We talked about how much electricity we're pumping in, but basic physics says that energy turns into heat. We're generating so much heat that air cooling just fans isn't enough anymore.
What's the alternative?
The next frontier sounds like total sci-fi, liquid immersion. We are moving toward a world where we submerge the servers into tanks of non-conductive fluid.
We're dunking the computers in a bath.
We're dunking the computers. It's the only way to pull the heat away fast enough.
Yeah.
The future of AI isn't just a glowing microchip. It's a bubbling tank of fluid in a warehouse in Virginia.
That is a visual I will not be able to get out of my head. The physical reality of the cloud is wetter, hotter, and heavier than I ever thought.
It definitely is. It's a whole new industrial revolution, and it's happening right in our power sockets.
Well, that is all the time we have for this deep dive. I hope next time you type a prompt into a chatbot, you picture that journeying through the grid into the GPU, generating all that heat.
Absolutely. Stay curious.
Thanks for listening, everyone. We'll catch you on the next one.